Pleasure to be here again. I was here once before, I don't know, 15 or 20 years ago. It seems like a long time and I forgot everything, so. Anyway, I'm very happy to be here again, and I appreciate the opportunity to come here, and it's wonderful to see so many people at this conference. I see that mathematics is alive and flourishing in Brazil, so that's wonderful. So I'm going to talk about one of my favorite subjects, which is algebraic space curves. And to start with, go back in time a little bit, sort of to lead up to the modern time. We'll start with Jakob Steiner. (1796 to 1863). Jakob Steiner was a farm boy. He grew up in Switzerland, and he helped take care of the sheep or the cows or whatever it was, and helped in his father's office a little bit. And he was totally illiterate until the age of 14. He couldn't read or write. He was useful, and apparently he was good at numbers. He helped in his father's office a little bit. But he didn't know anything until about age 18 or something. The Swiss educator Pestalozzi discovered him and took him to his school. And at his school, he began to show some promise in mathematics, and eventually he went to Heidelberg and then Berlin and became one of the greatest geometers of the 19th century. So if you don't know his name, it's good to know about. He helped set the foundations of projective geometry. And just to give you an example of how he worked, he used to write papers in which he would list like 20 different theorems in elementary geometry with no indication of proofs or anything. So I'm going to show you one. Here's one of his problems. You know, if you have a triangle, and I like elementary geometry too, so we'll do a little elementary geometry. Any triangle, if you draw the altitudes, that's the perpendiculars from the corners to the opposite sides, they go through a point like there. That's called the orthocenter of the triangle. I'm sure everybody knows about that. So here's one of Steiner's theorems. You take 4 lines in a plane, any old 4 lines. Okay, 4 lines. Any 3 of those lines make a triangle, right? That triangle has an orthocenter. So there's 4 different ways of choosing 3 lines. So you get 4 triangles. Each of those triangles has an orthocenter. And Steiner's theorem is that those four orthocenters, wherever they are, line a line. So if you get bored during the rest of my talk, you can try and figure out that one. Now, the reason I brought up Steiner is that besides being a great geometer, he taught in Berlin. He never married. He acquired quite a fortune by the time of his death, and he left a large sum of money to the Berlin Academy of Sciences to be used for prize problems. You set up a problem, and then people would compete and so on. So Steiner died in 1863. In 1882, the subject for the prize problem was a study of algebraic space curves. So there were 3 entries into this competition, and substantial papers of several hundred pages on the theory of algebraic space curves, and they were submitted anonymously. So each one had a Latin motto on it, and then there was a sealed envelope with the motto on the outside and the name of the author on the inside. So the judges looked at these 3 papers. They decided that 2 of them were worthy of the prize. They'd share the prize. The third one was not quite up to that standard. So they opened the 2 envelopes to see who won the prize. One was Max Noether, perhaps better known today as the father of Emmy Noether, and the other one was Georges Halphen, Frenchman. And they did not open the 3rd envelope since it didn't win the prize, so we don't know who the 3rd one was. It's a nice little puzzle for a historian if you want to research that. So Noether and Halphen each wrote an article of maybe 200 pages on the theory of algebraic space curves. So that's where my talk can begin. And what did they do? They just called them algebraic space curves. We today would call them curves in projective 3 space. So to describe in modern language what the subject is, you have a curve contained in a projective 3 space. And for us, we've put it over an arbitrary algebraically closed field K. Of course, they implicitly talked about the complex numbers, though they never mentioned the complex numbers. So think of an arbitrary algebraically closed field. And a curve is a one-dimensional subvariety defined by polynomial equations. And for the moment, let's think about a non-smooth, an irreducible non-singular curve. Irreducible means it's just a single piece, and non-singular means that it's smooth. It doesn't have any crossings or corners or anything. So that's what they were studying. So what did they want to do? They wanted to classify all of these curves. And in Noether's book, for example, he classifies all the curves up to about degree 20. There's a degree. See, a curve has a degree. The degree is, if you have a curve like this and you cut it with a plane in 3 space, it'll cut in a certain number of points, and the number of points it cuts is the degree. It also denoted by d. It also has a genus, G. The genus is a somewhat more subtle invariant. In topology, if it's over the complex numbers, a curve is also a compact Riemann surface, and its topology is a sphere with G handles. So G is the number of handles topologically. In the algebraic sense, you can define the genus this way. If you take, well, I have to make a slightly technical notation. If O of 1 is the hyperplane bundle on the projective space, and you take the O of 1 restricted to the curve, and you look at its global sections, only twist it by n, then that's equal to the dimension of the spaces is dn minus plus 1 minus g for n sufficiently large. So that defines g. You look at the you take the hypersurface of degree n cutting the curve, that makes a linear system. You look at the dimension, and for n sufficiently large, it's given by d times n plus 1 minus some number, and that defines the genus. Anyway, you can just think of the genus as some number that's associated to the abstract curve. The genus only depends on the curve as an abstract thing by itself, while the degree depends on the embedding in P3. So Noether made this classification up to about degree 20, and that's the beginning of the classification of space curves. Of course, it's progressed a certain amount, so the purpose of my talk is to sort of say, what's happened since then? How has the subject become more refined, and what has modern algebraic geometry contributed to this problem? And that way you'll see some of the techniques of modern geometry that come in. Yeah, I also should mention that Noether was mainly interested in these irreducible non-singular curves, and furthermore, in his calculations, he always assumed the curves were general in some rather undefined sense. I think probably general meant that whenever you made an estimate of some dimensions of something, that it came out to be what it ought to be. Nowadays, we're not satisfied with just studying general things. We want to know about all curves, so, and including special cases. So why should we, if we're interested in non-singular curves, why should we consider any other kind? Well, there's several reasons. So why consider singular curves? So a singular curve, what can happen? The curve can get double points, or it can get several different components, or it can get multiple components. Why should we consider those? Well, one reason is, let me illustrate already in the plane. If you look in P2, projective plane, the curve in the plane is defined by one equation, f of x0, x1, x2 equal to 0. So the homogeneous coordinates would be x0, x1, x2, and you look at a homogeneous polynomial of degree d, and that would define for you a curve in the plane. Well, if you take sufficiently general coefficients in this polynomial, you'll get a non-singular curve. But if the coefficients become more special, well, then you might get something else. So think of degree 2, for example. Degree 2, what do you have? You have a quadratic equation in 3 variables. The general one is going to give you something non-singular, a conic. But it might degenerate into 2 lines. and that's also a quadratic equation. And it might even degenerate into one line counted with multiplicity 2. If you took the equation x0 squared equals 0, that's the line x0, and then you count it twice. So in terms of when you think of a family, if you think of all the plane curves of degree d as making one family, then to complete that family, you should include these special cases when it degenerates. So that's one reason for considering singular curves. Second reason for considering singular curves, let's see. Oh yeah, so let me introduce one of the techniques that Noether used a great deal in his paper. If you have a curve C in P3, it lies on various surfaces, of course. You just take any surface that, if you look at in modern language, if you look at the ideal of the curve, that is all the polynomials that vanish in the curve, you take one of those polynomials, that'll define for you a surface containing the curve. So if you take two surfaces containing the curve, if you write C is contained in intersection of two surfaces, F and G, for example, then this total intersection will consist of the curve C plus something else. There's usually something else left over. So it's, this is equal to C union something or other C prime. And this is, Noether called it the Restkurve, which means the remainder curve. So we could call it the remainder curve, or in more common modern terminology, linked curve. So if you do this construct, you start with a curve, you just take two surfaces, and then you get another piece over here. So that curve is considered to be linked to the original one. And it may happen, even when the original curve is a very nice irreducible non-singular curve, it may happen that when you take a couple of surfaces containing it, the linked curve may be singular. So that's another reason for including singular curves, because you see, Noether's idea was to study a curve by taking surfaces of low degree as possible, and then hopefully the C prime is even lower degree. So that way the curve C gets related to something at a lower degree that he's already studied before, and that helps the classification. But that lower degree curve might be singular. See if I can give you a simple example. Yeah, well, the simplest example would be to take a curve on the quadric surface. We can work backwards. Let's work backwards. The quadric surface, you know, it has two sets of lines on it. And any curve on the surface meets these two sets of lines in two numbers, which gives you a bidegree. So if you have a curve in the quadric surface, it has a bidegree AB. So let's look at curves of bidegree 2, 4, for example. So that means it's linearly equivalent to 2 of these plus 4 of those. And in this family, there are irreducible non-singular curves. So you can find a curve C here. It has degree 6 and genus 3. So that's a very nice irreducible non-singular curve. But if you take surfaces of least degree containing this curve, it's already in the quadric surface. You take a quartic surface. So call the quadric surface F, and then take a quartic surface G. That makes a total of degree 8. This is degree 6. It leaves left over something of degree 2. And what is it? The quadric surface cuts out a curve 4, 4. So you're left with 2, 0. And what does 2, 0 correspond to? It corresponds to 2 lines on the quadric surface. So 2 lines that don't meet is a reducible curve. It's not irreducible. So that's the simplest example I can think of a irreducible non-singular curve where the best possible linkage here gives you something reducible. This also gives you a way of understanding this curve here, because you can start with the 2 lines, and then you can take a quadric surface, and quadric surface containing the 2 lines, and what's left over will be one of these. So Noether used that technique with great success in this study. Okay, now I want to talk about some of the ideas that appear already in Noether's paper and how they've grown since then. There's the idea of a family of curves. So what do we mean by a family of curves? Well, I think I'll give you one illustration over here. If you look at plane curves of degree d, for example, they are given, each one is given by a polynomial of degree d in those three variables, has a certain number of coefficients. And as you vary the coefficients, you can think of the curve varying, and that makes a family. So that gives a good sense, a good meaning, sense of meaning to the word family in the case of plane curves. It's not quite so obvious in three-dimensional space exactly what you mean by a family. But those guys in the 19th century, they sort of took it for granted. They said, oh, of course, they move in families. And then they felt perfectly free to talk about the dimension of the family and whether a certain curve was contained in the family or something. But if you think about it for a minute, see, the trouble is, here we have just one equation to deal with. So it's very easy to talk about a family. If you have a curve in projective 3 space, it requires at least 2 equations and usually more. The case of 2 equations is a little special. That's called complete intersection curve. In that case, if you vary the coefficients, you'll get a family. But a general curve requires 3 or 4 or more equations to define the ideal of the curve. And if you vary the coefficients in that, you won't get a curve anymore. So it's not quite so obvious how to define the notion of a family. So even though they took it for granted, you know, that's one of the ways mathematics progresses is something that was obvious, well, accepted, let's say, by the earlier guys, becomes questionable later on. Exactly what is a family? How do we know there's a family? And what's the definition of a family? So let's think about that for a minute. There's actually 2 different modern methods, that is to say 20th century methods of defining a family. So I'll mention that. So the first method is something called the Chow variety. And the idea here is if you have a curve in P3, you want to cook up a point of some space that corresponds to the curve, so that that space will act as a description of the family. And I don't actually remember the exact details of how it works. I think what you do is you take a complementary dimensional space, so you consider lines in P3. And the lines in P3 are parameterized by a certain Grassmann variety, which geometers call G13, meaning one-dimensional things in projective 3 space, whereas algebraists might call it G24, it corresponds to 2-dimensional vector spaces in the 4-dimensional space. Anyway, this thing is a certain quartic, dimension 4. It's a dimension 4 hypersurface in a projective 5 space. So to each line, it corresponds a point in the Grassmann variety. Now, among all those lines, mostly a line will not intersect the curve. If you have a curve here and a line there, they usually don't intersect. But sometimes they intersect. So inside the Grassmann variety, you can consider the subvariety, let's call it Z sub C. It's the collection of lines such that the line intersect the curve is not empty. So to the curve, we associate this subvariety of codimension 1 in the Grassmann variety. And it turns out this subvariety is defined by one equation. So we can write down the equation of this. F of ZC, one equation in 5 variables, and this is called the Chow coordinate, Chow coordinate. So in this way, you associate to a curve a polynomial, and of course, not every polynomial is going to correspond to one of these, but certain of them will, and that way you get a certain variety over there, which sort of corresponds to the curves, and that then nearby points in that variety means you've got a family. Now, what happens to the notion when you do with singular curves? With this particular approach, when you have a singular curve and you specialize it, if it's one of these, you just get that curve. But if it's multiple, you get an integer coefficient. So what this actually parameterizes is cycles in P3, and a cycle is a summation with integer coefficients of curves yi. Think of yi as being irreducible curves, and ni as certain integers. So if the formal sum of integer coefficients is called a cycle, and this Chow variety parameterizes cycles. So the sense in which you get families is families of cycles, and the non-singular ones are fine, but at the edge of the non-singular ones, the completion is just these cycles. So in this case over here, you'd get this one like that, and that one that, and this would simply be 2 times this line 0 with the coefficient. So that's one approach. The other approach, which is preferred now by modern algebraic geometers, has to do with the theory of schemes. By the way, to date this, I can't date it exactly for you. Even though it's called the Chow variety, I think it was partly discovered by van der Waerden and Chow, and that would be in the mid-20th century. I don't know, 1940s, 50s, somewhere around there. A little bit later, Grothendieck came along and completely rewrote the foundations of algebraic geometry into the language of schemes. So he talked about schemes, and a scheme is a structure. It looks like an algebraic variety, but there's a structure sheet, and the structure sheet is allowed to have nilpotent elements in it. So these are quite a bit more complicated. For non-singular curves, it's still the same thing. It's equivalent to what we talked about before. And if something is singular, so long as it doesn't have any multiple components, it's the same concept as it would be for a cycle. But when the multiple components come along, then it's much more complicated. So if you have a line in P3 with multiplicity 2, it's no longer just a line with an integer attached to it. It's a line with a little sort of a scheme structure of little infinitesimal elements along here. And something of multiplicity 2, these infinitesimal elements can sort of twist around. So there's lots and lots of different scheme structures of multiplicity 2 on a single line. I'm not going to try to explain exactly what that means if you don't already know. But so Grothendieck proposed something called the Hilbert scheme. And what that does is for each degree and for each genus, it gives you a variety, HDG, that parameterizes subschemes with the given degree and genus. So parameterizes subschemes. See, the interesting thing is that when you have a subscheme, you can define its genus, just the same way I defined it for the non-singular curve. And the nice thing about the family, the notion of family is then a flat family. And flat, the word flat here is a technical algebraic condition, which I won't try to explain, but it's just the right thing. It turns out to do the right thing. So that when you have a collection of schemes, you want them to be a flat family, and the flat families preserve the degree and the genus. So we get a parameter space for each degree and genus, whereas the Chow variety just preserves the degree. The genus gets lost. So everything of degree D in projective 3 space falls into one chunk of the Chow variety. Whereas on the Hilbert scheme, it's a little bit more sophisticated. So this is the preferred modern object to work with in talking about classification of curves. So that sort of explains what a family is. Now, what do we want to find out? What are the goals? What are the goals of studying algebraic space curves? Well, the initial goal was to list the possible degrees and genus and what the families look like. So if I make a sort of a shopping list of everything I'd like to know, what do we want to know? Well, first of all, we'd like to know all the possible degrees and genuses of curves in P3, all possible dg of curves in P3. What degree and genus are possible? Not all possible pairs. For example, the degree has to be a positive integer. It can't be negative. If the curve is irreducible and non-singular, the genus has to be non-negative. So that's already some restriction. Secondly, among all the curves of degree D and genus G, we'd like to know how many distinct families are there? How many families? You see, they form families, but it doesn't mean necessarily that for a given degree in G, that'll be for a big irreducible family. Not at all. And Noether was perfectly aware of this. The first example where it's for non-singular curves where it's not irreducible is degree 9 and genus 10. And in this case, there's two families. one family is a complete intersection of two cubic surfaces, F3 and F3 prime. You intersect two cubic surfaces, generally you get something of degree 9, it happens to have genus 10. And the other is by degree, let's see, what is it, 3, 6 on a quadric surface Q. This is by degree in the previous sense. That's also degree 9 in genus 10. And the interesting thing is that these two families of non-singular curves are disjoint from each other. If you specialize, you cannot specialize the curves in this family. You can't make a family of these which has a limit one of those, and you can't make a family of these that has a limit one of those. They're really two separate components when you look at non-singular curves. So one of the questions the old guys asked themselves was, how can we distinguish the irreducible components of the well, they didn't have Hilbert scheme. How can we distinguish the irreducible components of the families? And they try to find some other number to attach to it. You can distinguish these, for example, these two families, by the way, by asking what's the smallest degree of a surface containing the curve. So smallest degree of surface containing C. In this case, it's 2 because it's on a quadric surface. In this case, it's 3 because it's an intersection of two cubic surfaces. So that distinguishes them. But every time they found a new integer that distinguished the families, then they'd find an example a little further along where those numbers didn't distinguish it. So that seems to be one of those searches that will never have an end. I don't think there's a good answer to that. So how many families, and what are their dimensions of the families? So I think the search for a finite set of numbers or a small set of things to distinguish the irreducible components is hopeless. And in fact, there are various theorems that say that as the D and G get bigger, the number of components gets bigger, 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 bigger. So this question is one of those unsoluble questions in mathematics, which is still useful to think about, because if you have a distant goal, then you'll never get there, and you'll keep making more new theorems all the way as you work along. So as you go along. So I think, even though some problems will never have a solution, it's good to try, because as you go along, you learn more things all the way. So that's what we'd like to know. Let's see, what else would we like to know? Oh yeah, and then once you've sort of figured out what the D and G are and the family's dimensions, then you'd like to know what are the characteristics of the curves in each family. So describe curves in each family. This is a very vague word, of course. Describe could mean all kinds of things. In that example over there, I described them a little bit. Once you know this information, you know quite a lot about the curves, but you could ask for more. So that's what we want to know. So how far did they get? Well, for question A here, what are the possible degree and genus? Noether answered that by making explicit calculations up to degree 20. So Noether answered A for D less than or equal to 20. And Halphen pretty much did the same thing, but Halphen also gave a general formula. He gave a complete answer to A, which I won't write down because it's just a little complicated, and the actual formula is not so interesting. Halphen gave a complete answer to number A, which is the correct answer, but his proof was wrong, unfortunately. You see, there's two parts. One is to say that the D and G can be at most this list, and then you have to get examples that they all exist. Well, he got the correct bounds to show that to limit what the possible D and G were, but in the existence, he had the unfortunate idea that they could all be discovered and found on cubic surfaces, and that's not true. So this was finally proved, finally proof, by Gruizon and Pesquin in France. When was that? I think I might have written down the date. (1977) maybe? Oh no, 1982. On the 100th anniversary of the papers of Noether and Halphen. And their proof is rather interesting. They have to construct some curves on quartic surfaces, and they end up using some rather specific information about quadratic forms in characteristic 2. and then which integers they represent. Anyway, so that question is answered. This question here, the how many families and what dimensions are they all, that's one of these hopeless questions. And then the description, of course, one knows a certain amount in particular cases. So that's what we want to find out. Let me just mention one more of these questions that in this line here, that's still open, or mostly a little bit open. Once you know what degree and genus are possible, you might want to know something a little bit more. Ask furthermore, for each of those, what's the least degree of a surface? So I'll usually use the letter S to denote the least degree of a surface containing C. So for each curve, you've got the degree and the genus, and that. So you might like to know what are the triples, D, G, and S, of curves. Not only what are the degree and genus, but what surfaces do they lie on. And a very special case of this is the following question. What is the maximum genus of a curve of degree D that does not lie on any surface of degree less than S? So one way of answering this is you figure out the maximum genus of things that don't lie on curves surface of degree less than S, and then you go on to the S ones. So this question is known for S equals 2 and 3, and there's actually a conjectural answer to this question, but the proof is still incomplete. So there's lots of open problems. As every other plenary speaker has said, there's lots of open problems in this subject, so I'll copy them and say there's lots of open problems. So that's just one little example. Now, I want to say something about the methods of study. How do you go about approaching these questions? Well, there's several classical approaches. One is to start by studying curves on surfaces of low degree. Look at curves on surfaces of low degree. So if you take low degree S, let's say, if you take S equals 1, then you're looking at curves in P2, and that's easy. From our point of view, it's easy because for each degree there is a curve. So for each degree greater than or equal to 1, there is a curve. In that case, the genus depends only on the degree. If you have a curve of degree D in P2, its genus is determined. It's a half D minus 1 times D minus 2. And they form a nice family. They form an irreducible family because they're all given by polynomials of degree D with some coefficients. That's an irreducible family. The dimension of the family is something you can write down easily. It's just the number of coefficients of the polynomial minus 1. And the general one's non-singular, and the special ones you can figure out. So curves in P2 is very fine. No problem. S equals 2, we have the quadric surface. Now the quadric surface I mentioned already before. In this case we have a bidegree, AB. And whenever A and B are positive integers, there exist curves of that bidegree. The genus is determined by the bidegree. They form an irreducible family. And you can compute its dimension, and so that's pretty nice too. On the case of the quadric surface, I'm thinking about the non-singular quadric surface. If you want to include everything, you really should consider the singular quadric surface, the cone, a quadric cone, and that's a little bit different. But you can totally analyze them there too. For S equals 3, then we have the non-singular cubic surface. Here things get a little bit more complicated. But the structure of the non-singular cubic surface is very well known. It's obtained by taking a projective plane and blowing up 6 points. So you take a projective plane, you take 6 points in the plane, you blow them up, it embeds into P3. And because of that structure, the curves on the surface are classified by a group of order 7. So it's called the Picard group, big Z, pig of X equals Z7. you can write down a 7-tuple of integers corresponds to the degree of the plane curve and the multiplicity of each of these points. That makes 7 numbers. And for those 7 numbers, there's effective criteria to decide whether a curve exists or not, whether it's a non-singular curve. The genus is a function of it. And it works pretty nicely. Now, where it gets more complicated is if you really want to be exhaustive and consider the singular cubic surfaces, that gets more complicated. You know, there's singular cubic surfaces with isolated points and double lines and so on. There's quite a lot of analysis has been done, so that's pretty well understood. But the reason I'm making this list is that starting with s equals 4, it becomes impossible. And the reason is, for surfaces of degree 4, the rank of the Picard group can go anywhere from 1 up to about 16. So the curves on the quadric surfaces depend a great deal which quadric surface you've got, and it becomes hopelessly complicated. So Gruzon, Peskin, in their proof, did show existence of curves on certain quadric surfaces, but to make a complete analysis of all the curves on the quadric surfaces is essentially impossible, I would say. So this method is very nice up to small degrees, and then suddenly you run into insuperable obstacles. Yes?
Is it simple to describe a curve that doesn't fit on a cubic surface? It's simple to describe.
Oh, yeah. Just take P1 and take a curve of degree d, I can't tell you exactly which d, sufficiently large, a linear system, and embed P1 by a linear system of degree d into P3. That's a rational curve of degree d. As soon as d is beyond a certain number, which I can't tell you, maybe 15 or 20 or something, will not lie on a cubic surface. So here's another method of studying curves. This is the method by surfaces. Another method is to start with thinking about the abstract curve. You forget the embedding and consider the abstract curve. So B, consider abstract curves of genus G. And if you have an abstract curve, then you ask, how can I embed it into P3? Well, to embed the abstract curve, you have to give certain data on C. You have to give it a linear system. And then the linear system has a certain dimension. You have to decide whether it's actually an embedding or not. And this is a pretty good method because a certain amount is known about abstract curves. There's something called the variety of moduli, mg, moduli of curves of genus G. And this, again, is something that was understood and accepted by Noether and then the people in the 19th century, even though a precise algebraic definition of it waited till quite late in the 20th century. Probably Mumford's geometric invariant theory was the first time it was really rigorously defined algebraically, even though you can get it over the complex numbers using something called Teichmuller space. Anyway, there is a theory of abstract curves of genus G, and then once you have the abstract curve, you have to study what possible linear systems there are, and this has again been greatly studied. In fact, I think it's safe to say that in the 20th century, there's been more study of the abstract variety of moduli in linear systems than there has been of the question of space curves in P3, even though the problem evolved. Somehow or other, modern mathematics likes the abstract stuff. So there's this last semester, spring semester in Berkeley at MSRI, the Math Science Research Institute, there was a whole semester of algebraic geometry, and there were lots of talks about the variety of moduli of curves, and what its dimension is, what its codior dimension is, and divisors on them, and so on. So this kind of thing has been greatly studied in the 20th century. And this is an approach because then you start with small genus, you can analyze pretty carefully what's going on. So that's another approach, and Noether used both of these. And then the third approach is the residual curve I was talking about before. So the third approach, residual curves. Let me just talk about the residual curve again for a couple of minutes, because even though Noether used this technique, this technique has been greatly improved around the 1980s. By a better definition in abstract algebraic geometry. So if you have a curve in the P3 in the sense of a scheme, it's now possible to put the curve inside of two surfaces, F intersect G, and define the residual curve as a scheme. Furthermore, you can make an equivalence relation on curves if they can be connected by a finite number of such links. You say that C is linked to C prime by this operation. Then imagine C prime being linked to some other curve, C double prime, and so on, a whole list of them, Cn. And this relation then is called linkage, or lots of people use the French word liaison, because it appeared in a paper of Peskin and Spiro. They said they gave the abstract algebraic definitions of liaison in the terms of schemes. So this puts an equivalence relation on curves. This becomes an equivalence relation. So that in studying all the curves in P3, you now have this equivalence relation on them. You can ask, what are the equivalence classes? That's another great trick in mathematics. If you've got something that's too complicated to deal with, you put an equivalence relation on it, and then you study the equivalence classes, and then you study the structure of one equivalence class instead of all of them. So this is developments in the 1970s and 80s, principally. And I want to mention some of the results there. The nice thing about this equivalence relation is, and here's where I think by going 3/4 through my talk, I'm now allowed to introduce some more technical terminology following the usual colloquium. So don't mind if I write a few sheaves and cohomology groups. If you have a curve, it's a scheme inside of P3, then it has an ideal sheaf. IC is its ideal sheaf. It's a sheaf on P3. And we look at the first cohomology of the ideal sheaf and twist it by any integer n and take the direct sum over n and z. And what do we get? We get something, I'm going to call it MC. MC is the Rao module of the curve. It's a module over the homogeneous coordinate ring S, which is k of x0, x1, x2, x3. Furthermore, it's a module of finite length, because there's Sayre's vanishing theorems that say for n sufficiently large, it vanishes, and for n sufficiently small, it also vanishes. So it only exists in a bounded number of degrees, and it's finite dimensional each, so it's a module of finite length. So the main theorem in this part of the subject, Rao's theorems, are 1, two curves C and C prime are equivalent for liaison, this chain of things, if and only if their modules MC and MC prime are related by either duality and or shift of degree. So they can change, but they only change in two ways. One is as the grading. It's a graded module. The shifting of the module, the grading of the module simply shifts up and down, or the module is replaced by its k vector space dual. So that characterizes the equivalence classes. Secondly, for any finite length graded S module, M, there exists some non-singular curve, C, such that its module, MC, is equivalent to M by these same two statements up here, duality or shifting. So, in other words, you get every possible finite length module, and each finite length module corresponds to an equivalence class of curves, and each equivalence class contains irreducible non-singular curves. So that's a wonderful technique. So the third method of study would be, see, this sort of expands Noether's idea, because now we can sort of systematically study curves in these equivalence classes. And in particular, the equivalence class itself has a very nice structure, which I won't describe in detail, but just to say in general, if you look at L of M equals the set of curves whose Rao module MC is equivalent to M with shifts, this has minimal elements. Here's the equivalence class. It has elements of least degree, and then there's sort of an algorithm for getting all the other curves in the thing out of the least degree ones, and then plus an algorithm to find all others. Now, the bad news is, or the catch is, in order for this to be true, you have to allow curves that are not just irreducible non-singular, but you have to allow arbitrary singular curves, which are so-called locally Cohen-Macaulay. So you have to allow singular curves, allow locally Cohen-Macaulay singular curves as schemes. Locally Cohen-Macaulay means the local rings are Cohen-Macaulay rings, which simply means there's no embedded points. So you can have nilpotent, but no embedded points and no isolated points. So that's the catch. And this is another one of the reasons why we really have to include the singular curves in our study. Because if you try to do this just with the irreducible non-singular curves, it's a mess. You can't, I mean, you can still define the equivalence relation, but this minimal element in the algorithm for finding all the others just falls apart entirely. Because the minimal elements tend to be highly non-reduced curves. A little bit complicated as schemes. But it's a powerful method, and the fact that there's this algorithm for the others is if you simply know the minimal curve, then you can find the others. Now, of course, knowing the minimal curve is another problem, but let's not get into that. Yeah, okay, so those are the main methods of study. And now what I'd like to do is this works for individual curves, but I want to put this together with the notion of family. What happens when you try to study a family of curves, and what happens to the round module? So behavior of round module in the family. So let's imagine the Hilbert scheme over here. Fix some degree in G, and imagine here's our Hilbert scheme of degree G. How do the equivalence classes of curves under liaison compare, or how do they mesh with the Hilbert scheme? Well, what happens is that inside of any irreducible complement of the Hilbert scheme, you're going to have sort of strata corresponding to all kinds of different round modules. And even though, as I said before, there's no way to decide what the irreducible components of HDG are, there is a theorem of indecomposability, irreducibility, namely if you fix H, let's call it H gamma M. So M is a round module, and gamma is the postulation, which is simply numerical data about the degrees of surfaces that contain the curve. So that's a discrete numerical data, and the round module, and this is irreducible. So for each round module and for each postulation, which corresponds how far you've gone up in the equivalence class, it's an irreducible thing. So the typical Hilbert scheme is a union of sort of strata corresponding to these irreducible families. Now, how they fit together is a little complicated, because the round module can change, of course. There'll be M1 and some other M2 over here. If the dimensions of the components of the round module were the same, then you can do it as a nice family. But the round module is cohomology groups, and cohomology groups are not continuous in the family, they're only semi-continuous. So what happens is that the dimensions in here are going to change. And then this theory falls apart, and you need something more. So what you really need is if you have a family. Let's consider P3 over a ring now, A, and take a family of curves inside of here, flat. Then we need something. Just a second. We need something that plays the role of the round module for a family. And this is joint work in the last 10 years with Mireille Martin-Deschamps and Daniel Perrin in Paris. So you might think, if this is the morphism, let's call it pi. If there's the morphism pi, you might just think that you take R1 pi lower star of the ideal sheaf of the family C twisted by n and the direct sum of all of those, imitating the round module, just taking the higher direct images instead of the cohomology. But that doesn't quite work. That's not enough. So we had to invent something called a triad, which is actually a little complex of length 3, whose middle cohomology is this guy. And this thing here then characterizes liaison classes of families of curves. And furthermore, there's an algorithm. If you're given the triad down here, there's an algorithm for finding the families. And therefore, if you have the round module changing, you can find a triad which corresponds to changing round modules, and then those calculate these. So I'm very happy with those papers. I don't think anybody's read them because they're rather technical. It took 3 papers. It was going to be 1 paper. It eventually became 3 papers. So you'll find those if you want. So to end, I want to give you one particular example. I think it's always nice to see an example. And the other reason for this example is I've been talking about a number of things, but before you prove a theorem, it's usually a good idea to convince your audience that the theorem is not obvious. So that's what I do in my elementary geometry courses. Before we talk about the parallel postulate, I make a big effort to show them why it's not obvious. So I want to give you an example of these concepts that we've been talking about and why some of these things are not obvious. So let's look at curves of genus 3. Well, and I'll take the point of view of the abstract curve of genus 3 and how we embed it in the projective space. So here's C, an abstract curve. One case is there's something called the canonical sheaf, omega, and if omega C is very ample, if it's very ample, then it's going to give an embedding of C into P2 as a curve of degree 4. And conversely, a plane curve of degree 4, non-singular plane curve of degree 4, has genus 3. So in the plane here, think of a plane. Here's a curve of degree 4. The non-singular plane curves of degree 4 give you lots of curves of genus 3, and they correspond to those curves of genus 3 for which the canonical divisor is very ample. But there's another case, and that is the case when C is hyperelliptic. Hyperelliptic means a curve that's a double curve, that exists a double cover down to a line, P1. And there are hyperelliptic curves. For the hyperelliptic curves, the omega is not very ample and does not give you an embedding in P2. So in this family, these make a nice family, of course, because they're curves in P2. In this family, you don't see the hyperelliptic curves. And it's not obvious, at least I think it's not obvious, whether these form one family of curves or whether they form more. So even in the abstract variety of moduli, there is a theorem that says that the variety of moduli of curves genus G is irreducible. But that's a deep theorem. In the analytic case, it's known by considering the Teichmuller space. In abstract algebraic geometry, it was proved only 19-something or other, 70s or 80s, by Deligne and Mumford, using the theory of stacks, which is a frighteningly complex new development in algebraic geometry. So you could invoke the irreducibility of the variety of moduli to claim that the hyperelliptic ones were sort of specializations of the abstract ones, but it's not obvious at all. And from this point of view of embedding in P2, we don't see it. But here's something else we can do. We can embed these curves as degree 6 curves and genus 3 in P3. Now, if you look over the tables of existence of curves of D and G in P3, you'll find 2 different ways to get degree 6 genus 3. One way is on a non-singular cubic surface. They exist. And these you can obtain from this embedding over here by taking, if you take 6 points on the quartic curve, like that, and you blow up these 6 points, then that gives you a cubic surface. And this quartic curve in P2 then becomes a curve of degree 6 in the cubic surface. So these curves here give rise to those. In particular, these are not hyperelliptic. The second way you can make a curve of degree 6 in genus 3 is on the quadric surface. Take by degree 2, 4. I think that's the same one I mentioned a little bit earlier. That gives you something of degree 6 and genus 3, nice non-singular curves. And you can see it's hyperelliptic because you see you've got these 2 families. The quadric surface is isomorphic to a direct product of P1 cross P1. as an abstract variety. And if you take the projection out of the first factor, you get a 2-to-1 mapping to P1. So it's visibly hyperelliptic. So now we have all possible curves of genus 3 represented in P3. The non-hyperelliptic ones are on a non-singular cubic surface, and then the hyperelliptic ones are on a quadric surface. And again, I claim it's not obvious that the family A specializes to the family B. You see, these are not contained, they're not contained in any irreducible cubic surface. So there's no intersection. These two families don't have a common intersection. The question you can ask is, can you make a flat family of these specializing to those? Again, the answer is yes, but it's not at all obvious. You can't see the equations. You see, if you write down the equations, you're going to have a cubic equation here plus some other equations cutting out that curve. And here you're going to have a quadratic equation plus some other equations starting in degree 4 cutting out this curve. And it's not at all obvious that you can specialize one to the other. So how do you know, it is true, by the way, that there exists a family specializing from A to B, but how do you know that? One way you know it is by using the irreducibility of the moduli space. But there's another way. I'll tell you two other ways that are both, well, one of them is constructing the other. Another way is there's a theorem that says that any irreducible component of the Hilbert scheme HDG has dimension at least equal to 4D. This is proved using deformation theory, which I can't go into right now. But let's accept this theorem. The theorem was known to Noether, by the way, but his proof doesn't really stand up to modern ideas of what a proof should be. But so it's 4D. So if you compute the dimension of this family over here on the quadric surface, the linear system has dimension 3 times 5 minus 1, which is 14. And the choice of the quadric surface in 9 parameters, and that makes 23. And 23 is less than 24, which is 4D. So you can count the dimension of this family. You see that it's less than 4D. Therefore, it cannot be an independently standing component of the Hilbert scheme. It must be contained in the closure of something else, and the only other something else around is this one. So it has to be contained in the closure of that one. But this is sort of a very roundabout way, and you don't see the family yet. You don't see it at all. You just deduce its existence by this sort of roundabout method. Well, there's another method of showing the existence of the family, and that is to use which I've erased, to use the triads. This one here has a Rao module equal to 0. It's what's called an ACM curve. This one here has a Rao module M equal to the residue field in one place. And you can make a triad that measures families going from ACM to things with module K, and then in that triad you can see that there does exist a family going from here to there. But again, it's a little bit complicated to manage the thing of triads. So I hope that example will show you that some of these things are really not so obvious, and it's worth studying. So thank you.